you can also
yeah,
what we are talking about briefly, you know, so people know.
Yeah, just go over the
Yeah,
points.
oh, you already like. Okay, thank you. So one of the things, you know, that people now joining, Christopher, we are discussing about the new developments. One of the developments I have is that I'm going to publish. Eventually, I'll show, but in this particular video, I'm not going to show that, but just a description of how the Schrodinger equation and the fixed equation diffusion has a lot of similarities. So they also have the.
I have a quick question about that. So the Schrodinger equation is based on diffusion, isn't it?
Yeah, that's what I'm thinking, but it doesn't show. You know, I don't think anybody has taken up this particular aspect.
But I think that is the entire point of the Schrodinger equation. Now, this is not to undermine what you're saying or anything. Just
yeah.
So what? Remind me again. So you have the particle. We know exactly where it is, and then as it evolves in time, it becomes more diffuse. So I think what Schrodinger did was to say, well, a good way to model this would be to use the mathematics of diffusion. I think it was diffusion, where there was some equation that he focused on. I'm pretty sure it was diffusion, but it could be something else. So it's basically spreading out in volume as time goes on. So if you're noticing a similarity there, you're spot on, because I believe that he decided, well, I'm just going to take this equation and apply it here, and that's what you're seeing. But interestingly enough, you know, when we talk about diffusion and, let's say, fluid dynamics in general relativity, and so people have been applying certain types of fluid dynamics and then also thermodynamics as well to gravity, general relativity. And so that for a while there, they were talking about concepts which have definitely fallen out of fashion and because they've been disproven. One was the tired light theory. So the idea that space is some kind of friction that tires light out, and so that's been experimentally ruled out, I think, as well. But then there was another idea about diffusion, I think, sort of along with that. But it is a separate idea. So yeah, I mean, that could be one possible direction you could look in if you're going into diffusion. I'd have to look that up, and I'll send you on some links, because I was yes. So continue anyway.
Yeah. So I can reference that what you're sending, and then what happens then in that case, the psi, the wave function, becomes like a concentration. So it's like you can redefine wave function as a wave concentration. So the psi is actually like a concentration of waves that spreads out. So you have high concentration of the wave from the particle, right? Highly concentrated wave.
Yes.
And then it spreads out. It's the same idea. But now you look at from the physical chemistry aspect, how a concentration, how the diffusion occurs. But then what is the D? What is the diffusion coefficient? I found by using my previous thing and then comparing, you know, you have IH del by del T of psi equal to something times del square psi by del x square. I think it's M and all that comes there. And then plus V of psi. V of psi is the potential energy. Now, fixed equation is del square, del concentration over del T equals D, which is a diffusion coefficient, times del square, some concentration over del x square. So that's, you know, that's, so when you compare that, you convert the Schrodinger equation in the same form, the D becomes IH by 2m or something like that. So I found that, so in the error function, you put that value for, you know, the solution is the concentration equal to, you know, the initial concentration times the error function of x over square root of D, which is the diffusion coefficient, times T. So the D value, put that, and then instead of the concentration, you put psi, the same, value, and then you substitute for D from the Schrodinger equation by comparing it, and when you manipulate that, you'll be surprised that the M comes, M comes on top, and then if you say the V, then I can convert x and t, x over t, that becomes the velocity. And this velocity for vacuum, you can put c, and then you rearrange, you manipulate all the equation, you get mc squared inside. Then mc squared is the energy, right? And then you divide by h, which is the reduced Planck constant. That becomes omega. Then omega t becomes theta. So everything simplifies in terms of the theta. What is the theta? So I think, and then you put it back into the definition of error function, you get what a Schrodinger solution is, like this cos and sine, psi equal to cos and sine. But instead of going that one direction, you go in the geometric direction, and you say what that theta represents. A phase angle. You can convert to phase angle, and the phase angle is, because you are talking vacuum, is like the meniscus of the vacuum. So you have the vacuum which just spreads out like that, and then another type that spreads out, and our idea of superluminal thing comes in. So underneath you have that, and you have focus, two foci that comes from there, and that eventually forms like ellipse, but ellipsoid, in 3 dimensions, it becomes ellipsoid, and it can rotate. It can rotate because it has 2 foci, and it can rotate along that axis. But now it's sitting in the superlunar phase and is projecting into the vacuum. Now, this is where the egg aspect comes into picture. So the egg shape, when you actually calculate that foci, they are not symmetrical because of the superluminal thing is faster. So the foci is close thing, so it becomes more like an egg shape. And the egg shape, when it's it can flip, then because of Bernoulli effect, it can pop up through the vacuum and come into a subluminar phase. And when it comes to the subluminar phase, then you can rotate again. So there is a free rotation possible, the environment, and then it can sit there, and it can like a gravity effect. My feeling is that eventually there will be one like cone shape, the sharp edge of the egg, and the other one sitting on top. They produce what kind of like what Emmanouil is talking about, like a horn torus. So you have one egg, and sitting on that, and the sharp, and so the smoother edges, larger edges coming together. So they form almost like a black hole type thing. So singularity of black hole. So they produce, and they produce stability. They produce a stable particle, like Higgs boson or something like that.
So what is where did the foci originate from, though?
The foci is because of the meniscus, the vacuum side curvature, and when you project that curvature of the field into the field, it produces the foci.
Okay, that's interesting.
Because the geometry, the geometry produces that.
Okay, I'd have to see that, how that's done, because I mean, is the meniscus of the vacuum?
Yeah, so vacuum forms like a meniscus.
But isn't
forms like a meniscus between the superluminar and the subluminar.
With if you have the tangent space meniscus, the curvature on that is basically 0. So a projection from the edges of that.
It's very slight, very slight thing. It is not
on the very edge, like at infinity, you could have a very steep, like an actual.
Because the hyperbolic, right? Those hyperbolic.
Yeah. So, but for projecting from that, I mean, I don't know. I don't know where that would go. It would probably just go to infinity below the tangent space.
Yeah. The reason is
it would be because these things are at infinity anyway. They would be perfectly symmetrical. So
yeah.
So in order for any projection, they just cross in like a triangle, you know, equilateral. So I don't know where the foci would come into play. Would it be at the top, from the top of the meniscus?
Yeah, it will be far apart. It will be far apart. Yeah. But
the main from the top of the menisci.
Yeah.
What is the plural of meniscus? I don't know. And then if it could cross through the center of the surface of space, and then and meet at the bottom here, then you'd have 2 points, which could be your foci. Is that maybe something?
Yeah. So
okay, cool.
Yeah. But
I mean, so go on anyway. You had some other comments you made.
Yeah. The important thing is that now, instead of using what Schrodinger used, was he converted into Euler equation. It's essentially Euler equation, and it gives sine and cos functions, Euler formula. But instead of using that, use the error function as such. The error function has two things: error function complementary and error function. So error function complementary, like psi could be error function. The psi prime, you know, the conjugate of that could be error function complementary. So when you draw that curve of the error function, they look like meniscus, slight meniscus. But the error function is, if we put the values of error function, they actually taper off very fast, which means essentially they become flat very fast. So essentially they will be flat, but at the edges, you know, they spike up. Like very small value of the error function is the only one that a high value. When you go a little bit more, the value of the error function drops like anything. You know, they essentially become flat. If you use the values of the error function. So instead of using the sinusoidal, you know, the trigonometric aspect of the Euler, use the error function itself, and you solve that, you get this meniscus. So, you know, but the Schrodinger didn't go in that direction. He went to the direction of sinusoidal thing. That's how we got the sinusoidal things and everything. That may be true inside. You know, what I'm saying is that the outer edge will be like error function, but inside the fluctuations, 0-point fluctuation, all those things, the quantum mechanical thing, where the wave is fluctuating and creating the cloud, where electrons can form, for example. So these are part of weak theory. These are not strong theory. These are part of the weak theory, because I'm saying that potential energy is 0, which means I have another conjecture where I say that true vacuum could be where the potential is 0, but there's also a force vacuum which is higher up. So that potential is not 0. So that solution of that is different. So that gives the strong aspect. But this true vacuum gives the weak aspect, where fermions, like electrons and positrons, will form. And that makes sense. You know, what we are talking about, solution, the error function solution, is for weak theory, for the electrons formation, and things like that, which is like waves, cloud, you know, it forms like clouds. So a highly concentrated thing, but it spreads out, it diffuses out and forms cloud. And then you find the probability of finding that inside that cloud. So this is essentially what one of the things about the quantum mechanics is that, you know, and then Heisenberg uncertainty principle comes into picture also, that you cannot really measure the position and the momentum at the same time. So there's a measurement problem.
Yeah, so when you're saying strong and weak there, you're not referring to strong and weak forces. You're talking about what, high and low energy? No.
Yeah, so where they are created. Like in true vacuum, what I'm saying is that electrons, the fermions, can be created. Whereas the false vacuum,
energy, then, is it? If it's a false vacuum, would be higher energy, is it?
Higher energy. So it can create the strong nuclear, like hadrons, even hadrons or mesons can create eventually combining. So I have I have another conjecture.
What is the Bernoulli thing? How does that work?
Oh, Bernoulli. Okay. Bernoulli is this shape, right? So the Bernoulli is acting at the bottom. So like you think of like a parachute coming down or something, you know. The actual thing, initially you think of like the Apollo, the module, right? The module looks like that, right? Apollo module.
Yeah.
What is it called? I think it's called a module.
Yeah, I think
there's another term for it. Yeah, there's another term for it. But
the lunar lander, maybe?
Huh?
Not the lunar lander.
For example,
the thing that looks like a cone.
Yeah, cone, but it kind of flattens out at the bottom.
Yeah, the thing that landed on the Earth, right?
Yeah, because they went up there, and when they come back, you know, when they come back to Earth, you know, it detaches. It detaches all the whatever rockets, everything, and this particular module, which houses the people, right?
Yeah,
it comes down and flashes onto the sea, and there these people, the Navy people, go there and collect them, right? So it's something. I call it module. I think there is another term for it, but that looks like that. You can see that when the shape is like that, the gravity acts. You can say, you know, gravitationally it falls down, but the shape is upside down.
Yeah,
like this one. It is like your, you know, parachute or not parachute, more like a hot air balloon. So it can go up because it acts like a wing. You know, the top is flat, acts like a wing. So the air, you know, the Bernoulli, the air has to move fast, and then the pressure drops, so it lifts it up. You know, so you can use
like pressure and like density and all of that earlier. Yeah. So similar to what I was saying on the hypersphere, everything gets. So I had to issue a correction on that, hadn't I, earlier from what I'd said that what was this? I was saying that the speed of light was constant on the sphere, but that's incorrect. It's getting slower as you go up because the metric is getting smaller, right? So then
it becomes more dense.
The area between the lines of the metric gets smaller as you get to the North Pole. So so everything's getting smaller, including light, essentially. So light has to travel slower, but when it's projected back out onto the tangent plane, it becomes the correct size. Everything has the same size, and so time is the same. So light is constant on the tangent space, but then we can say that time slows down as you go up the sphere. So it's not just that things are getting smaller as they go up. It's getting slower as well. And it's getting slower because this is my thinking, is that it's getting more dense. So there's more pressure. So all processes slow down. So that's why when we look at, say, supernova type 1A supernovae, the further away they are, the slower they appear to, you know, explode and do whatever they're doing. So yeah, so that could explain that, where the time dilation is coming into effect, even though it's not really, doesn't seem to really be a time dilation. It seems to be sort of a time compression is the wrong word as well, but there's something else going on there. It's almost like yeah, so when that happens, you have the metric is preserved, but the time is slowing down. So then the question is, I suppose, if we were to travel out there, would we what would we see? Would we think, oh, everything is slower out there? Well, no, because we're also a process, and we would slow down. So we would start counting a normal amount of time, rate of time for the supernovae ticking over out there. But looking back to where we are in space, if there was a supernova in our vicinity, then we would see that moving at twice the speed. That's what I'm thinking. So, but then this idea of density, then if you're talking about traveling, you know, at super or luminal speeds, sorry, it's like it's equivalent to moving up into this dense region, or alternatively, it could be equivalent to a dense region moving down. Because let's say you were traveling at the speed of light past the Earth, yeah? Then the Earth is at the lowest point essentially of the hypersphere, whereas all the dense parts are up here. So if you're traveling at the speed of light close to the bottom, there's no density. All the density is up here. But if like you could imagine a bubble detaching from that, coming down, and then you're trapped inside the bubble and you're moving along. So there's a couple of ways of doing that. I think one of the ways, I don't know if I have, the very kind of famous images of an elliptic curve that we were showing before. So yeah, something like that. But then really I'm thinking maybe more like a Clifford torus, where so it looks flat, but then kind of inverts and craft gets subsumed into that. So we can look into that as well. It might be an interesting thing. And there's also technically 4 sort of states within that, which coincide with what I was talking about earlier, that you can travel at the speed of light. Let's say this is all hypothetical. Then once you go beyond the speed of light again, time goes, you move into like imaginary time. Then if you go again, you're moving half the speed of light again, I think. All right, I have to look into this, the actual mass. But then you're moving into like negative imaginary time, and then finally negative time, just normal time, and then you go back to proper time, if you will. So that is so then it's saying that, so it's basically like you're accelerating into, and time is going normally into the future. Then you move into this new imaginary time, which is difficult to comprehend what that is really. And then you start going backwards, because now you're backwards in imaginary time, and then you're going backwards in normal time, which means that you just arrive back where you came from, kind of, in a sense. But you are in a new, if you were to actually do that, you would be in a kind of a new universe. But it's hard to know if it would be a new universe, or would it just be this universe, like identical to this universe. But it seems like you'd no longer be moving. Like the faster you go, the slower you'd go, until you just stop. So I don't know, that's what I'm looking at. And so this same transformation, like what could we call that? Like a 4-part transformation from speed of light to imaginary time to backwards imaginary time to backwards time, is the same. If we have the torus, like this is the torus, and we're at the top part of the torus. As the torus inverts, you wind up in instead of going around the outside, let's say your vector is pointing around the outside of the donut torus. When it rotates the first time, you're now going around the one of the rings. So you're a smaller distance. You're also at right angles to the direction you were previously in. So all of that conforms very well geometrically with what we know to be imaginary spaces. And then you keep going, you're going to come out the other side, so you're going to be looping around the other part, and that will be backwards imaginary time. And then there's an inverse again. Oh, sorry. No, I skipped one. I think backwards imaginary time is going around the inner tube. So instead of the vector pointing along the outside of the donut, you're now pointing along the inside of the donut, but in this possibly in the opposite direction. I'd have to check. So that's backwards time. And then there's the other side of the, the way a torus, like if you were to take a cross section of a torus, it would look like 2 circles. So now you're on the other circle, and then finally you're back to the outer circle. So those would be the 4 transformations using a Clifford torus. So That could be interesting to look into.
Oh,
so is that, you mentioned something about density in your model as well, to do with this egg, and would you like to, is there a major difference to what I'm talking about, or?
No, actually, so when you my different calculation a few weeks ago, I think I mentioned to you. I think you are now also conforming to that. Is that your hypersphere? You know that we think is high. That also you are agreeing. No, it may be more like egg shape. It may not be. It may be non-Lorentzian, whereas the tangent plane is Lorentzian. That's what we are coming to. That's what my calculation showed that it should be. So that is like vacuum, you know, like a vacuum meniscus.
Yeah, well, last week I was at, remember we were discussing it, and I was kind of asking you what your, you know, because I was like, well, I think initially I said that time would slow down on the sphere and wouldn't on the tangent plane, and then I reversed that. And then last week I was saying, what do you think, Rajan? Like, you know, but it's not something, I don't think you can just, you know, if someone were to ask you that question and you've never thought about it before, you're not going to be able to provide an answer just straight away. It's something you have to sit down and think about all of the ins and outs. So I kind of realized that, and then so the last couple of days I kind of just thought about the different aspects, and I came back to the conclusion. I was like, oh yeah, okay, so the first formulation I had was correct. I have no idea why I inverted it. I suppose, oh yeah, I think I was trying to deal with supernovae and stuff. You know, I got all this new information to do with supernovae and quasars, and I was like, all right, so I had to solve this in a model. So I just said, you know, I wasn't interested in like what's the truth of like time on the sphere, or I was just like, solve this problem. And then that's solved now though with the time dilation of the quasars. So it's good to put things back in order when you're done, you know. It's housekeeping, but it's good. I think I said it to you a few times and you were like, you sounded a bit doubtful, so that also kind of made me, you know, question what I was saying. So go ahead anyway. You were saying
So, so the physics sometimes, you know, you have like two alternatives, right? That's why the math is useful. Like, luckily, I could, you know, I couldn't answer completely, but now I know after doing the, you know, I was doing error analysis separately for information, things like that. Suddenly it dawned up on me when I looked at it. Oh, they look very similar to Schrodinger equation. Somehow, like a eureka moment I had, and then I do that, everything falls into place, and then I get the vacuum. I said, then your tangent plane should be vacuum, which is a Lorentzian thing. So now I could answer your question. So I know that from the math, it has to be Lorentzian, the tangent plane. So
great. That's good.
So that's a good mathematical proof. You can say a backup.
Yes.
For your argument.
There's some interesting stuff here, and it looks like it could be possible to actually make, you know, definite statements like that. Is the light constant on the plane or on the sphere? Yeah, we can work that out.
Now
and then there's other questions then, you know, because there's obviously disagreement with John and Gerd about like relativity on the sphere and the tangent plane. What is rotating? What is the center? Is there a center? These kind of issues. So I think those are maybe they're like just as difficult, maybe even more difficult to solve. But you know, you have to be very careful, because if you say, I think from one perspective it seems very obvious, but then you can look at it from a different perspective and say, well, looking at it like this is also possible, you know. So we need to work that out and make sure, you know, solve these problems and then just move on. But it's looking like, from my perspective, I'm thinking if we have this an isotropy in all the galaxies, that seems to be a very big indication that there's this there's an actual proper orientation to the hypersphere. But it's still not enough to say for sure, because you could travel out from that and, well, there's issues to do. Remember, we were talking about if you rotate the sphere, what happens to the metric? And it seemed like last week we were saying that the sphere can rotate, but the projective point won't rotate. It will just sit there. So that would seem to suggest that the metric and the point at infinity are locked in place, which would imply that there is a proper orientation. But then again, if that goes to infinity and there's like, you know, a potentially infinite amount of space, like up there towards the point at infinity, as you can imagine, because we can divide space down smaller and smaller and smaller, then when you get to the point at infinity, you know, you could have galaxies out there, but they're just like, this is the point. They're just, when you rotate, if you go, it's hard to describe, but if you were to go like out to infinity and rotate out there, they're just like rotating past this point at a very small scale. So they can all reorientate around the point at infinity on a very small scale. So basically the universe is non-orientatable, and that's also totally fine. That can work as well. So from a mathematical perspective, you know, you could say, like Gerd is talking about, that essentially, and John and myself have mentioned, of course. So I'm here at the center of the universe in my location, because, you know, the universe is infinite in every direction, but where you are, it's the same, because the universe has to shift slight amount, but because it's non-orientatable, it just warps around the central point. It's the projective point, I mean. So it's not a problem. That can be done as well. So
oh yeah.
Yeah.
No.
It does seem like, though, the anisotropy, possibly a big piece of the puzzle. CMB could be another one. The axis of evil, as it's been called, it's a terrible name, but CMB alignment, and yeah, other things, but those are the main ones, I think. You know, go on anyway.
Yeah. So one of the encouraging things is that, you know, I mean, I'll tell about a couple of other people, but before that, the encouraging thing is that, you know, I say the potential energy is zero, right? That's for the true vacuum. That's the vacuum. But what you're talking about, the hypersphere, may be in the false vacuum, because it may have V not equal to zero. So but that solution is much more complex. See, the original Schrodinger equation, you have to solve it by considering particular solution. The particular solution is this error function. Then you have to come up with the general solution. I mean, it's a complex thing. You know how to solve like forced oscillation, right? It's like forced oscillation. When you have force, you have simple harmonic motion, that you are the wave equation, but the wave equation has the second order equation. But then when you have forced oscillation, like you have resistance, you know, so I have to look into that. So you put equal, the other side is not equal to zero, but equal to F, which is the force of the air. Then you got the solution of the force of oscillation, wave theory, from wave theory.
Yes.
You know, so that's very fundamental.
That is separate to what you were talking about earlier. I suppose you were describing the Schrodinger equation earlier in some detail there.
Yeah. So the Schrodinger equation can be solved two different ways. One of them are V equal to zero. But you keep the time, and see, what Schrodinger did was time dependent, time independent. Instead of that, you solve potential energy zero in one case for the vacuum, and then you get the error function solution. And the other case, you say the V equal to not equal to zero, and when you solve it, you know, it's like forced oscillation, or a forced because of the force. That you get I'm sure you probably will get a false vacuum. So the false vacuum, the potential is higher, and that eventually is what is creating the hypersphere, which probably shapes now, like I was said, like egg shape. And then your makes sense.
Well, I'm not saying for sure it's an egg shape, though.
That you have to figure out. When you solve it, you know, that's why the math, the solution, when you solve the problem, geometrically, you will get egg shape. I mean, that's what I'm thinking is, but the math is much more.
I think you can do it either way. I mean, I think maybe the like an egg shape with a very pointed top, like I mentioned earlier.
Yeah.
I mean, if we think about that from a, you know, I was just thinking about it kind of in a, almost as a metaphorical kind of like a useful concept to think of what's going on. Because like I mentioned, it kind of reminds me of Kip Thorne's illustrations of black holes and stuff. But if we think about it practically, like let's say that this is the top of the sphere or egg as we're calling it, and then we have a projective point at infinity. Now this line is moving tangentially to the top of the egg, so this point, whatever's at this point, will get projected to infinity, parallel to the tangent plane. But then look, as it moves down, it's not projecting anything between here and the sphere.
The discontinuity.
Yeah, that's a major problem.
So that could be a black hole. See, so you could have egg like this and the egg like this, right? So you have black hole there, you have wormhole that coming. You can also think of a wormhole.
Yeah, I mean, it's an interesting idea. You could have like the singularity, then void, and then what's this called? Event horizon.
Event horizon or something. Yeah.
Well, would event horizon not be the same?
Event horizon. See, if you have black hole there,
I thought you said
event horizon will be.
Yeah, so it just seems like
right next to it.
But then why, you know, that seems a bit strange because you'd have a singularity, then nothing, then event horizon, then.
But I don't know if it's nothing or not. That's something we have to figure out. Because if you have event horizon,
certainly none of the matter of the universe will be projected into the point between the singularity and the event horizon. You would have like a lot of the strings that we were talking about, that the projective lines will be there, like an infinite number of those, with no actual matter. So you'd hit the event horizon, vanish, and appear in the singularity in this model, like, which is a bit strange.
Yeah, but one of the simple things is that suppose you have a event horizon, right? If you look at the arrow, so the arrow points down from the event horizon towards the tangential plane, whereas the arrow will point towards the black hole. So that is the event horizon will be like the interface where the vector changes direction. You know, it flips. So the vector is pointing here, whereas from the event horizon going closer to the black hole, the vector will point towards the black hole. So you have interface. So it's like an interface, and that interface is the event horizon. So that will make sense. And your point about the time going imaginary, negative imaginary, and negative is based on, it's also, you can think about the 4 quadrants where you plot a complex plane, right? So your eye here and a real plane here. And also, it's like the Wick rotation. You know Rodney Bartlett? He's an Australian. You may have seen his papers. He sends me the papers from us. He also has some very good analysis now of a lot of the things. And he puts in the RG, a lot of things.
Huh, I don't know. Okay. You're roboting
the 4 quadrants.
Yeah.
Huh?
You were roboting there.
RODNEY.
Oh? No, I'm just saying you kind of froze there for a bit. Yeah.
Oh, okay. Now can you hear me?
Yes.
Okay. So I'm talking about Rodney, RODNEY, Rodney Bartlett, BARTLETT. He's an Australian.
Yeah, I've heard his name. Yeah.
Yeah. he has good analysis. A lot of things he sends me also, because he looks at my thing and we have communication. A lot of things. But his main basis is a Wick rotation. And the Wick rotation is very similar to what you're saying about the real plane, about the imaginary, the negative imaginary, and the negative. You know, the four quadrants make the Wick. That's a Wick rotation. So I think there are a lot of things, similarities that's coming into picture. I think it's all different piece of puzzle falling into place. I think your thing, a lot of this is, once you accept that Laurentian thing and the law, then we are much more closer. Because I'm coming from this side, you are coming from that side. Seem to be matching.
This is it. Well, there's definitely
there are some questions about hypersphere.
Interesting. And then, so I think we covered a lot of those things. The other thing that I recently came across that I think I mentioned earlier was the like prior to streaming this was twistor theory from Penrose. So he's talking about again, it's kind of projective geometry, but this time you're projecting from a four-dimensional complex sphere, you know, down to lower dimensionals, so that you get spinners in general relativity and kind of Minkowski space-time. And I was saying that so it's plausible to have these other kinds of projective sphere within the anamorphic universe model that are sort of separate to the main model, almost like they're backup files that are being imported in. But the actual spheres don't exist in our universe or anything. They're just there for calculation purposes. That seems reasonable. But so let's say you have these. So I was thinking about these spheres a bit more, and complex four-dimensional spheres with like just even the results of these embedded in the four-dimensional sort of surface or three-dimensional surface of the 4D hypersphere would be what? So you have these spinners, which are two spinners, obviously, which means you rotate them once 360 degrees and they don't come back to their original positions. So if I was just trying to extrapolate that back onto the anamorphic universe model, model, and you know the way. So we start with we don't start with a singularity in this model. We start with like a very dense kind of group of matter, stars and galaxies, that then get rotated out and then anamorphically projected, stereographically projected into infinity. And then, as I say, towards the end of the universe, then they'll I was trying to work out how long this is going to take. Is it going to take millions of years or whatever? Because I'm saying that it only took a 24-hour period for the entire universe to expand. That's my guess on this. It seems like a reasonable.
The time expanded. You are saying that it was 24 hours. Now 24 hours is equal to billion years. It became, when it expanded.
The expansion took 24 hours.
Yeah, it was very fast. It was very fast. Now it's slowed down.
In a sense, it didn't travel at all because it's all projected from the sphere. So it's like I was saying, a disco ball's, the light seems to be projected on the walls. It's moving very fast, but it's actually not moving at all. So that kind of thing. So then when it gets out, it's at 180 degrees now, and then it's going to rotate back, but the rotation back is going to happen way faster than 24 hours. I think it's going to be like, it's going to be very fast anyway. I haven't worked out how fast yet, but possibly a lot quicker. Anyway, it's interesting. So, but the point is, once it gets back to the center, that's 360 degrees rotation. But I'm thinking because of the whole hypersphere thing and the spinners and the relationship there between projective, what will come back in won't be the same as what left. It'll be totally inverted in some sense. So that could be quite a positive thing. We don't exactly know what kind of matter that is or what. I don't know. There could be just different effects all around. It's just an unknown area, or it could be very similar. again, I just don't know. But I know for certain that what comes back is not the same as what went out, in some sense. Only after 2 degrees would you get back to the very same thing, which is very similar actually to the rotations I was just talking about you go faster than light, twice, you know, by the time you get to twice the speed, you're back at where you started. But you know, you had to go through these 4 different compartments first, like we're saying for I minus I, 1 minus 1. So there seems to be this constant double cover and reference to this. But then that's obviously going to come about because of what we're just talking about with 1 minus 1, I minus I. You're always going to get that. So that's pretty cool. Anything I could show you some other stuff that I've been working on if I just share my screen.
Only I want to comment on that a little bit. Why it rotates, why it flips. Yeah, why it flips it maybe because of the edge shape. And then if you look at like hourglass, we use for time, right? You put sand in them, you know, for playing games, things like that. And suddenly it occurred to me, it will be just like that. And so, you know, we flip it and then you can, you know, each time maybe like 10 minutes, whatever, and you flip it and then it like a you know, sand. So that singularity is inside. It's not really a singularity there. There's a hole. So it's not a real singularity. So that's the point I want to make.
Well, that's it. Yeah. So like another analogy for this whole system, obviously, is like a snow globe. You know, everything's like sitting there and you rotate it. It all gets like muddled up, you know, and then so it's like a bit of like a snow globe universe in a way. But that was like the thing. You know the way I was talking about every point in the universe has 7 or 8 dimensions attached to it because 4 on the hypersphere, 3 on the tangent plane, plus the point at the projective point at infinity, if you like, or at the North Pole. But then I was saying that you have this sphere, and then on top of that is a second sphere with a second tangent plane above that. And then so a line that passes through the tangent space and through the hypersphere to the projective point will just go out the other side and hit a second hypersphere and a second tangent plane. So then you need to add another 7. So that would give you 15 points in total, which all, you know, 15 is this kind of number that comes up a lot. You'll see it in relativity.
Dimensions? 15 dimensions?
It will be technically 15 independent dimensions. So you'll see that in modular forms as well, which we'll have to apply to the system. But the reason why I bring this up is because of the point you just made, which is that it's got a very hourglass kind of, you know, that whole system with the line through, or you see that this other thing that I've been thinking about. Another kind of an analogy you could use, I don't know if I've really brought this up, is that the point, projective point, and the whole system is very much like an eye, you know, like a human eye.
Yeah.
I can show you a lot of diagrams that sort of.
Yeah, I think I also mentioned about the eye aspect. I was thinking quite a lot that it is the eye that's looking out on us. You know, like the black.
We've said that. Like, it's just what the point you made there about that it's not actually a, I don't know, singularity.
Singularity. It's not a singularity.
Like a hole, which is like, you know, like an iris.
Definite size. Yes, a size. So it's not a singularity.
I don't know.
I mean,
it
depends. It depends. I mean, you can look at it. Maybe a smooth black hole. You know, it's not necessarily a singular black hole. Possible.
Yeah, well, I mean,
that's something we have to figure out.
A lot of sort of, like sort of esoteric kind of directions you could draw this into. Well, I was just thinking from the point of view of, you know, being sort of an analogy. The human eye has what's an iris, a pupil, you know, like the hole, the aperture that allows light in. Yeah. And obviously, if you have this projective point, it is a letting light in some sense into the system. So I don't think it matters. It doesn't have to have an extent. I think Gerd is saying that it has to be on the order of the Planck length and can't be any smaller. I don't actually know about that. You could probably go smaller. I don't see why not. But it's not something that I really. I don't know if it needs to be beleaguered too much, but maybe if it's going to have some impact on like the physical ramifications of the model, then yeah, brilliant. I was trying to think about it a bit more. I think it probably does go down to. I mean, at least you could say maybe the aperture is like Planck length in size. That doesn't mean that there aren't smaller scales. So therefore, you would say that the aperture does have a size. You know, it is like.
But there could be crossings. There could be crossings at the aperture because it can the field can cross each other. So it may look like singularity because of that, because of the crossings.
Oh, I think it will. Yeah, I think it will.
Because it can go this way, this way, this way, this way. So all the crossings together, you know, that form like a point, and that point will be the point of singularity, possibly.
Right. Yeah. So it's interesting.
The other aspect is that black hole may be actually a false vacuum. That's another thing. So that stuff erased up is it could be a false vacuum. Like I said, the false vacuum and the difference between false vacuum and the true vacuum is the potential energy. Potential energy is zero, the true vacuum. Potential is not equal to zero at the false vacuum. And that's why we have vacuum decay and all those things. Yeah.
Well, I don't know if, I mean, I suppose it's plausible. I was kind of ruling out false vacuums and vacuum decay in this model because that is like a theory about how the universe could end, isn't it? Whereas
vacuum decay, but like Emmanouil saying, like he pointed out a YouTube.
Well, like if we look
a little while ago,
I suppose that these are possibly two separate models that we're discussing, because the one I'm suggesting has a very definite sort of end to the universe. That's sort of well, like I say, you know, the universe begins with a 180-degree rotation, so it makes sense that it ends with another one. You know. Yeah,
they're like egg. Egg has to rotate. If it's egg shape, it has to rotate.
It's not egg shaped, though, Raja. It's a sphere. I mean, otherwise you're going to have this. You're going to have You're going to have the universe goes out,
rotates, you know,
and then there's going to be a definite boundary to the universe where everything gets really compacted. Then there's going to be nothing, and then there's going to be the point of it at infinity, which is going to be like a circle around the universe, which contains no information other than what is like. So yeah, I don't think like an egg shape. I think it's perfectly reasonable to, like, if we're talking about a singularity,
more like hourglass.
Again, that's an hourglass is not going to have any singularity because it's like a thing, isn't it? So
I mean,
I think you could have two spheres, one on top of the other, that are contacted at like one single point.
That's a point.
Yeah, but it would have to be like a singularity. It couldn't be like this.
Yeah,
it would have to be.
I mean, it could actually. What happens is that singularity could be broken and produce a wormhole. You know.
Oh yeah, no, I think that seems reasonable. Like if you were to travel, so this is the odd thing. Like if you were to travel somehow over the surface of the hypersphere, you know, it would be like traveling in that direction, let's say, to infinity, and coming out this direction, the other side, instantly. But then let's say there's obviously another dimension that we're leaving out, which is in the fourth dimension, which is straight up. So if you could go straight up through the singularity point, well, when maybe not straight up, but instead of going straight through, you kind of go. I suppose you have two options.
At an angle.
Yeah, or flow up into the next. So it's like an X, isn't it? You kind of go up diagonally. Then you
because
will.
Like a torus. It's a four-dimensional thing. Torus that you can flow into each other. It may be like torus. Maybe like torus there, right there. But we think in singularity could be torus. Torus means there's a continuous flow. You can flow in and out and come back again. So can go to the other side, right?
Yeah.
So in that way, that makes sense.
That does make sense. There could be like some sort of boundary between them, and then if that like boundary was removed, you could have mixing between the two universes. And I think the potential between the two, like if there's a denser state on top and a less dense, then you'd have like a flow.
Yeah.
And then over time there would be, you know, they'd reach equilibrium. And what would that be? That could be like your false vacuum. That could be that would be a bit like a catastrophe, really.
The wave concentration. That's why psi as a wave concentration will help in that. What I'm thinking. I have to, but the other solution for the false vacuum is more complex because it's like force thing. So I had to. Now I had to concentrate. I want to just publish probably this one and then think about that. Eventually, we will have a paper together. Eventually. And then the book together. We are going to publish a book together also eventually next year. And in between, we'll have like the videos that we are talking about history of physics. So we have a lot of things on the pipeline for next year, I think. The book and the video series that will form eventually a movie. But we'll have this video history. So I'm already thinking about 10 different episodes. The first episode, I'm thinking what really led to classical physics. That may be one of the things the first video will be. So I have a title for each video. That's the first one, and then depending the title could slightly change depending on how the debates go, because some people may be more expert in talking about the time before Galileo. And then what led to Galileo? There may be some inner things that happened in Europe and other places that led to Galileo. So Galileo also might have gone through. I think many of the scientists have two sides. One is inside, one is outside. So, there are a lot of stories in between, but not all stories are correct. So you have to go into details. There are a lot of stories that was spun.
True.
Lot of like Newton thing, everything. Like a lot of stories were spun around, but the actual things may be quite different. Than what was what we see as even in standard textbooks. Sometimes could be little contorted. Then
I do like maybe the idea of the pointed egg thing being maybe some sort of, although I don't really know exactly how it functions but it is kind of interesting from a objective point of view.
And then you have the so if it is a heavy, highly dense thing, and on top it's going to flip. I mean, even the egg shape will flip. So why the flipping occurs?
The egg shape being that's
why does it flip? 180 degrees, and there may be a reason for that. That's all. Well, it could be a forced vacuum also.
Yeah,
it could be a forced vacuum also. But
no, I don't know.
I think we can figure out. I think
it's
we can
interesting. I mean, it seems to be slightly different to the other stuff you're talking about with the foci and the Bernoulli effect. Might be a little bit on the. I mean, it's interesting. Might be a little bit on the complicated side, though.
Yeah, exactly. I also think that way.
Again, like, the sphere is embedded in what exactly? Pure, like a sea of pure energy, maybe? That could be like a much higher infinite energy source. Like I was
Laurentian energy.
Like John, you'd have, like these pores where you have the sources and the sinks and energy is moving into the sphere and out of it again. But maybe not. So hard to know.
We have to think about dark energy, dark matter.
No, we don't need. You don't need dark energy.
You don't need that,
Because think about it. If there's
light energy, like if you have Laurentian energy, which is a light energy.
We don't need to think about dark energy because there's dark energy is meant to do what? It's meant to
expansion of the universe.
Right, but in this model, there is no expansion of the universe.
Yeah.
Because it's an illusion.
It look like that,
on the anamorphic projection from the sphere. So
but another point,
but the dark matter is still a possibility.
Yeah,
that's something that I'm going to have
rotation
to get
curve, right?
What?
That's because of rotation curves. Dark matter is because of rotation curves.
Yes, yes. So that's still something that needs to be that will be in the model, I think, because I mean,
you have
there's
different spheres.
Evidence for that not to include it.
So it's quite possible you have one sphere, right? After some time, that sphere disappears, another sphere forms. So it's like another universe forming, like that. So the dark matter is the interplay between that. That's like a what you call like a mediator, or what is a transistor. So when it disappears, when the particular sphere disappears, that becomes dark matter, and that feeds energy or energy back into the next sphere, the energy. So then that forms like that. So it can form multiple universes like that. So that's a possibility.
It's I mean, you could have
the dark matter is the one that is in between.
You could have an entire dark matter universe, and that would be no problem. Yeah, and then you could also have an entire matter universe. I'm pretty sure.
So the matter is.
I mean, it probably wouldn't be as interesting as either one separately wouldn't be as interesting as the universe that we inhabit, is the other thing.
Yeah.
I can show you some other concepts maybe that I've been working on that are a bit more abstract. So, I mean, I do like what you're talking about. They're kind of more, well, I'm not
mathematically provable. So I want to go one step at a time.
When we talk about analogies, like if I'm talking about the universe like an eye or something,
Okay.
I think it was relating that back to Christopher Langan's idea that if God can't see you, you kind of don't exist, sort of thing. So.
Oh yeah. And
let's say. What?
Kipton you mentioned also. So these two people we can keep in mind. Rodney Bartlett and Kipton.
Oh yeah, well I know I was talking about Christopher Langan.
Okay, Christopher Langan, yeah. This one, elliptic curve geometry.
Yeah, elliptic curve geometry. So this was something that was part of the previous slideshow that I removed because.
Oh, okay.
The
anamorphic universe.
It was too much information and. Now, hang on a sec, actually. I did, I'm just going to stop that and start again. So I think we need to do that. Let's try it. So the problem I was having last time was I didn't share the entire screen and I was doing the, okay, so that present. So you can see that, can you?
Yes, yeah.
Yeah, so I didn't share the entire screen when I was presenting last time. So the idea is, this is the universe, all the galaxies in the universe and all. And then when you do the rotations of the hypersphere, so this is pi divided by 4 rotations, see there's an asymmetry as a result of like a Mobius transform. There's pi by 2 and the asymmetry is worse. You can see there's more galaxies floating around up here. So that's just one idea. So basically, now the order of this information is wrong because it was my first attempt at this formalism. But so we take Mobius transformations of the projection from the hypersphere. So this might be in the YZ plane, for example. We'd have this kind of rotation matrix, which would rotate the sphere like we saw in the previous slide to create some sort of Mobius transformation. And then, I mean, obviously there's a link between Mobius transforms and modular forms, and there's a link between modular forms to elliptic curves like we see here, which are also actually projections from unit spheres and other spheres. So obviously you can go from the modular forms that I spoke of earlier which can be used, you know, to create the elliptic curves. But here we have it the other way around. We have an elliptic curve with these coefficients creates, you know, so we have this elliptic curve over a rational field, and then we can get the modular form of that, which gives us this Q polynomial, and then get the coefficients of that. And that would produce this. So, but the problem is doing it the other way around, going from the modular form to the elliptic curve really seems to be a process of trial and error. Also, there's an issue with, you know, if these coefficients get in any way big, the computation time just gets very difficult to convert them. So this is like the wrong order of things. But let's say you were to start with all of these modular forms are generated by like an element of SL2C. So 2 by 2 matrices in the complex, over the complex plane fields, integers, if you like, with determinant 1. Yeah, so we could use those as rotation matrices to create our 4D rotations. Then we can also use them, take them as the coefficients to create modular forms, convert those into elliptic curves, and then get the group theory of that to create elliptic curve cryptography. So the idea would be every point or every rotation in the universe would have a unique modular form associated with it, and a unique, well, maybe not a unique elliptic curve, but because you can have more than one modular form associated with an elliptic curve. And then from that, you could generate some sort of code, elliptic curve code from the results. Another thing we can do is take the modular form that you just saw in the previous example. Suppose if we look at the progression, you have this modular form, and we go towards sort of infinity kind of things. It's interesting to look into more, but then this is even more kind of infinite tiling of the hyperbolic sphere based on the modular form. So you could ask, well, what is this kind of structure? Is it, you know, maybe this is time going off into the past, present, future, you know, like this. But then that would imply that there are other dimensions of time stretching off. Maybe these are probabilities, or they could be, you know, instead, you know, if this was one cell of the universe and this is the neighboring cell, so this is like point x10, this is, or, you know, coordinate 10, this is coordinate 20 and 30, so on and so forth, which would mean that if a particle was moving through space, it would go, you know, you'd see it coming this way, and then we get closer, and then it would move further away into the distance, which is really just very much similar to what would be happening with time anyway. So I don't think any of that's really correct, but it does appear that if you were to take, you know, an infinitesimally small portion of the hypersphere, it does look like there's an infinite hyperbolic space associated with it through the modular forms. However, it's questionable whether it is actually an infinitesimal small part of the hypersphere, because SL2C, while it's an infinite group, is not actually, you know, they are integers, I believe. Maybe you could take a lot of the equations. Well, if it's C, it shouldn't be just integer based, should it? It should be any. But for some reason, they come out as integers anyway. That's certainly SL2Z does anyway. Maybe SL2Z doesn't, so it should be right. But the modular forms are actually based on SL2Z, and they seem to be integers, counting numbers, so pluses and minuses. So if we were to take them and do rotations with them, it's not clear like if there's an infinite number of rotations that can be gleaned from that process, or if there's overlap. So, you know, like in group theory, if you rotate by 90 degrees and then in the like XZ plane, and then 180 degrees in the XY plane, and then 90 again in the ZX plane, let's say, then that's going to be the same as just rotating 90 degrees in the ZX plane, or the 180 degrees in the ZX plane. So you have these kind of, you know, basically like group theory, that you multiply two different matrices together in different orders, you get to different places, but a completely different set of matrices will bring you to the exact same place. So that would mean that there would be an infinite number, let's say, of SL2Z matrices that would bring you to the same rotated point on the sphere, which would imply that there would be like an infinite number of modular forms that would correspond to that point, and therefore an infinite number of elliptical curves, and therefore the whole process is useless. You see, there'd be no unique solution to any of this. But then again, maybe there is unique solutions. They'll just have to be looked into a bit more deeply, I guess. Possibly using, you know, you could use like a quaternion expansion of the SL2Z matrix and then apply that to all 4 different rotations of the hypersphere, and then mod that by 2 pi or something, and that might lead to like unique rotations, might not. Then again, maybe SL2Z will lead to mostly unique rotations, but even if it does, they won't be infinitesimal. That's another point, because since it's not continuous, it's SL2Z, they're integer values, there will be a jump between one integer value and the next. That's why modding out by 2 pi might be useful, because it will bring back like a continuous, you know, because it's over an irrational number. But if it's SL2Z, then any rotation will be unique up to a certain value. There'll be like a range of values that will always be equivalent. So you'd be rotating into a region of space that would correspond to a unique modular form. So that's something to think about. Yeah, so, but an interesting part of like the modular forms that we looked at here. So if you go along the edge, like the critical line, you see that we're going through the different values of pi here. And then, so out here, this is just rotation, you know, through the different values of pi in a circle. But out here, we see that there's some sort of perturbation of the rotation. So it's, you know, if we were to graph this, instead of just a normal sine wave, we'd get like some sort of Fourier transform wave. Like basically what I mean is an addition, how do you say? Yeah, like lots of different waves added together, you know, so superimposed. So that looks like this essentially, though. If we were to project it onto the hypersphere, then, you know, at the south pole, when it's projected onto the tangent plane, we would have a waveform that looks like this. So this could be the momentum of the particle at that general area of where SL2Z brings the rotation of the sphere to. Initially, I was thinking it would be an exact point on the sphere, which I suppose it's an exact and unique point on the sphere, but that might not be actually correct unless the 2 pi modular rotation might restore that, but doesn't seem likely. And this is also going back to the Heisenberg uncertainty principle, which was modeled on the stereographic projection of the unit sphere, which also contains these Fourier and Fourier transforms. So this kind of goes back, you know, we have the hypersphere model, the twistor sphere, which is projective geometry, and then the Heisenberg uncertainty, which is projective geometry again. So, but at a lower dimension. So it seems like it's just lots of different kinds of projective geometry, which is interesting. I think Gerd was talking about that as well. So you could also have, yeah, I don't know if I want to go into that really. Projective. I think that's really it for that. And there was some other stuff. So this is just more the actual calculations for this. So you have SL2, you know, these are examples of matrices from SL2Z, just random examples. And they can be converted into elliptic curves like these over the rational plane. You can also see how they are. These are the same ones again. They can be transformed into quaternion real number matrices like that, which can be used as 4D rotation matrices when multiplied by all 4 of the 4D rotations. Or we could just multiply by these guys. It'd be the same thing as vectors. 4D vectors. I'm not entirely sure which method oh yeah, I took the 4D vector method like I just said. And that would produce these modular Mobius rotations. So you can see what I was talking about. This quite looks like an eye, doesn't it? You know, you have the dark patch here and the larger kind of rotation patch. So each of these then is meant to be like a unique rotation of the, particularly that one, of the hypersphere, and then just standard projected, I think, onto the tangent plane in this case. So there's the Mobius transformations from SL2Z. Then this is a placeholder of what they look like when they're converted to elliptic curves. And then we can select the first 3 dimensions of the 4 vectors, because that's kind of what we need for a 3-dimensional space, and project that down onto the tangent plane. So we're now on a 2-dimensional surface, which will give us different coordinate values, which we can then, these are, how do you say, these are float values, essentially, like decimal values. So if we multiply by 10 and take them as an integer value, we can then start creating elliptic curves out of these, which is useful. This is code I got from elsewhere, because this is dealing with, this is elliptic curve cryptography, which is a slightly advanced topic, I would say. Well, not just slightly, but fairly advanced. So you have to get your elliptic curve, and then you add in your points, which we got from SL2Z, and that gives plus your over your field, which is some sort of prime number. In this case, I think it's 71. And so that gives you these, this is like the subplot. You see those, there's your finite field, essentially. And then we add in more of the values from the SL2Z matrix to get this line. So then we can differentiate the line to get like minus 3.2. We could run this again with a different set of values. So I'm not sure how wonderful this method is, but if I were to change this to 43, which is another prime number. Run this again. You know, we get a different kind of, what is it, winding on the torus essentially, and a different, what's that called, like rise over run, a different slope basically of the line. So yeah, it could be useful. You could talk about maybe encoding information at each point on the hypersphere in this manner. So it could be another kind of compression, or this could be, you know, so the whole thing seems to be more like a coordinate system where instead of just coordinates, you have a modular form for each coordinate. You also have like a unique waveform for each point, for each modular curve, which would be the critical line. Not sure if I have an example of this. There's an example of when the equation gets too big, when the integers are too large, it just won't do it. So you see, these are the Q polynomials of the SL2Z matrices, which are very similar to what we normally. So it's just the same thing, but rearranged with the different degrees placed in. Then you need to find the elliptic curve of this. So that's trial and error, like I said. But the interesting thing about that is the elliptic curve requires either 2 or 5. I think it's 2 or 5 or 3 or 5 coefficients. So that will be 4 of those coefficients are the SL2Z items, sort of elements, and then within the matrix, and then the other 4, then that gives you your rotation. So then your 4 become essentially the point on the hypersphere plus the point at projection, which gives you 5. So that point of projection will always be, you know, either 0 or 1, depending on how you want to formulate it. Usually put in 0, but one will do as well. So we have polynomial rings. So yeah, sure. A lot of this is maybe this one. What's going on here? Okay, so that's a bit slow. I think we also have the results of that quantum gravity thing. There was a problem with that last time, and I fixed it. These are just general stuff. So hopefully this works this time around, but I'm not sure if it will. Oh yeah, well this is like 4D gravity type thing. We're talking about the meniscus and surface tension and that kind of thing. So it's using, oh wait a second, this is definitely running too long. Okay, that seems to have not worked. Hey, how's it going? So I think there was a problem there. How much of that did you see before it?
I saw your.
Jen, I think you're muted.
You're trying to.
Am I muted? I'm muted.
No, now can you hear me? Yeah, I had muted. I was on mute. But
yeah, you were on mute, and then my the volume on my computer was down as well. So basically, that's the I was just running like loads of notebooks there without really
quantum gravity. I saw the quantum gravity thing.
Okay, good. I'm gonna have to kind of sit down and how do you say? I'm gonna have to re-look at that.
Yeah, we can stop in another 15 minutes if you want.
Yeah, well, I'd have to look at the notebook again to check what it's actually calculating, because it looks like it is. You know, I haven't looked at that in a while, but I remember I fixed it, and so, but maybe we'll go into that another time. So yes, so that's the kind of stuff I've been looking at recently. But I mean, you know, it's all kind of much of a muchness. I don't think it's that great or anything. I think that the real research is more on the sphere and the cosmology. These are just sort of
that seems to match with what we are saying. Mostly, like I said, this like I'll give you a 6-dimensional manifold, virtual, manifold dimensions of time, and that's. I mean, you are talking about already the 4 different times imaginary time, but I think there are 2 more. I mean, when I add that, of course, when I transform it to this thing, it's it transforms to a different kind of thing, but transforms to a 6-dimensional thing, and then you have 4-dimensional toroidal space. So it comes to 10 dimensions in that sense, but then of course that's based on one sphere. Suppose you have multi-sphere, then your dimensions will add up. Like we are saying, the one sphere, or the one or that hypersphere, what you call it, or that disappears. Another one forms. The dark matter is, ensuring the transitions. Then we are talking about more dimensions. In that case, to describe that, we need more dimensions, perhaps. So that makes sense. But that's more complex. But what I'm thinking right now.
Yeah, I mean, do we really need any of that?
Yeah, that's all question.
I mean, it's cool, if we wanted to, there's a lot of stuff out there that uses 10 dimensions, like there's string theory and all of that. I mean, basically, like if we came up with a model that somehow explained all of string theory or something, but then that implies that string theory is a problem that needs to be solved, which is not actually what string theory is supposed to be. String theory is supposed to be a method to solve the problems that we're trying to solve, not something it's not an extra problem that we need to solve, Oh, well, I suppose you could start from the answer and work back to string theory,
Yeah.
But that's not like, we're not in any way likely to do that. I mean, certainly there have been a couple of things that have cropped up which say, oh, this could apply maybe to string theory or this, or even like that torus with the windings and all that kind of go back to string theory.
Yeah.
So it's cool because there's loads of cool mathematics there, and there could be links, but like I said, it's unlikely that it will pan out that way. Again, so when for instance, when Christian's talking about 6 dimensions and yourself 6 and 10 dimensions, it's like we're kind of calling back to string theory and saying, well, string theory must be correct, so we need these dimensions. But if we're able to solve everything or speak about everything without any of those things, then then there's no need to bring them in necessarily, technically, But that's not to say that they couldn't be there. But you need to have like really good justification for saying that they are there, I think. Or like if your model is set up in such a way that it just that all of that kind of falls out of it, and that's great. So
yeah, the new method, I think, with error function, I think I have more promise. I think that will eventually explain string theory. My feeling is that string theory is like your hypersphere, a lot of strings going around it, all over the place. Your torus and everything. So you can think of many strings going through, and those strings will have higher dimension naturally. But really, you can all compress to 4 dimensions eventually.
The thing about the lines that are coming from the projected point, they're all going to be what, 1-dimensional, because they're lines.
Yeah, so they're strings. They're like strings in some way.
Right, but yeah, or you could say 1-dimensional or 2-dimensional, depending on how you formulate that, and then but they're crossing through a hyperdimensional space, which is the 4-dimensional space. Well, that's really it then. They themselves don't have 4 dimensions, but then neither do the strings in string theory. String theory's strings are, well, they're considered 2-dimensional because they're a loop, but
yeah, they're either loop or open. Either they're loop or closed or open.
Right, but they form as they move through space-time. Let's say they form a closed tube if they're a loop, So that's a 2-dimensional manifold, then, that closed tube. So that's why sometimes they would say, like, of the 10 dimensions in string theory, 2 of those dimensions belong to the string, even though the string is technically 1-dimensional. I know, it's complicated.
Yeah. So you can think of mesoscopic example, like we use like twine. We actually wind it almost like a torus, right? So that we can pull out that twine or a string.
Yes.
So actually you can buy it. You can buy it from a shop. And they look like torus. They are wound around and they are continuous, and goes inside out. And then you can pull out the strings. So string theory may be something closer to that aspect.
Yeah. Like, I didn't like the idea of using strings to model particle interactions and all. I think that's worth looking into. Even though, like, I did watch a really good talk there by, what's the name of that physicist? Is it Voigt? Do you know?
Voigt?
Yeah.
Voigt?
Yeah, he wrote a book called Not Even Wrong.
Oh. Is it VOIGHT?
WOIT. Yes, WOIT. It's annoying. It's I literally just watched the show just a little while ago, and his name is gone from my mind. But Voigt, anyway, I think it's Edward Voigt. But he's a mathematician, and he's also working in with twistors and stuff. And he seems to think that, well, he basically wrote this book, Not Even Wrong, which showed that there's huge problems, for example, in what is the thing called? String theory. So it's on that Theories of Everything podcast with Kurt, I don't know how to say his surname, J. Mungle or something. And
string theory is good in explaining weak gravity and strong gravity. I use the concepts, not the string theory itself.
Sorry, just to interrupt you there, I got the name Peter Voigt.
Oh, okay.
Yeah, pretty good. So
is it W? Peter?
Yeah, WOIT. That's correct. Okay, Rajan. Is there anything else we need to cover? I'm not going to do any more presentation.
Yeah, I think mainly that is it. I just want to also say that Rodney Bartlett I'm talking about, he also talks about Mobius transformations a lot. So I think it all fall into place. But I think what I'm going to develop initially, the tangent plane is your Lorentzian, but it's also vacuum from my model. And that's the first paper I will have. That's all I will talk about. The second paper I'll try to introduce what if the potential energy is not equal to 0. Then you have false vacuum. And what happens then? You have the strong thing, what's happening in that one. So I just touch upon that, whatever mathematically you can advance it, but it will become more complex. The actual solution may be quite complex. That may be one reason that Schrodinger, for example, may have gone in that direction, but then he deviated and he created linear transformations, things like that. I don't know. So all these we'll figure out, what is going on, and whether that solution will give us, the hypersphere or the what you call as the egg shape or the hourglass type of thing. Something we have to look for when you solve the geometry of that. Whether it's solvable, I don't know whether it will be a closed form solution. When v not equal to 0, there may not be any closed form solution. So that creates problem. Whenever there is no closed form solution, I am very, very, skeptical, because it doesn't give physics. You do then you have to do something else to understand the geometry, like you are done. You have to do that.
Yeah.
There's no other.
What is the definition of this closed? Was it closed form solution for
solution? Like the original Schrodinger equation does not have Schrodinger with the time and space and the potential energy. I don't think there is a closed form solution. They are not able to solve the problem. So they have to introduce some constraints to solve for hydrogen atom, and that's how they come up with all the orbitals, different shape, like dumbbell, all the shapes of the orbit. But you cannot solve the Schrodinger equation for higher, more than hydrogen atom. You cannot solve the closed form. Closed form is like you have f of x equal to, 0. You are able to solve it completely. You are able to come up with the roots of the equation. Right? What are the roots? Then that's closed form. But you cannot come up the road. But instead, you have to do approximation, numerical analysis, or something like that, or
just because it's so complicated that there is a solution, they just don't know what it is.
Well, there may not be any solution, because, like I said, when I do the general transforms, it could be like a black box. Black box does not have a closed form solution. So if you are like higher order differential, a lot of them don't have closed form. So you have to do many numerical methods, to solve the problem. Like you start with iteration, right? You say x equal to so and so, and then you iterate it. So you got, a numerical values, at different things. But you are not solving it algebraically. You are solving it numerically, So that's what a closed form solution has algebraic solution, whereas the non-closed form solution has numerical solution.
But like trial and error, basically.
Trial and error, yes, exactly. So it doesn't give the actual physics, because we don't know the actual curvature, all those geometries. We cannot, we are assuming things, and then we are trying to get, say, the problem, the iteration is that you need to have convergence, right? So you use many techniques like the Cauchy convergence or the p-adic value, things like that, to converge the solution. And I use something like function. That's much more, I studied a couple of courses in numerical analysis, and I did a little bit of programming. But there are many methods in that, like the Newton-Raphson, different types of methods. But the one I liked is, suppose f of x equal to 0, you can say x equal to f of x, and or x prime equal to f of x prime, and you can iterate. You just put the value of x and put in that value of x in the other. Like your x square plus x equal to 0, for example. You can say x equal to x square plus x equal to plus 1 equal to 0. Then you transfer both sides. So you can say x equal to minus x square minus 1 on the other side. You put a value for x, then you calculate for minus x square minus, and then you iterate around that, so then those values, the error goes close to 0, then you have a solution for that.
Oh, sorry, when you're saying iterate, do you mean iterate?
Yeah, same thing.
Oh, okay.
So use a computer program. Ideally, you can use a computer program to,
because when you say iterate, I'm thinking of like titrations or something.
Oh yeah, iterate. Yeah, there are different ways of saying. Now, in the US, we say differently, and even US depending on the place you are. Some people say iterate, some people say iterate.
Oh, iterate is what you're saying.
Yeah.
Oh, okay.
So iterate. Yeah, iterate. Also, I don't know how.
That's very American. Yeah, where the pronunciation's always is a little bit different over in the.
Also, when you go in US, different places they have different accents. Same thing.
Yeah.
Yeah.
So that's interesting. Let's. Are we? Do you want to stop?
Yeah, we can stop that now. Okay, thank you. Yeah, we'll continue next week. Yeah.
Yeah, good.
Yeah, we can stop the live stream. Want to stop the live stream now?
Yeah, I can't sign. I can't stop it because I'm not signed in.
How?
What?